Hello and welcome to this video. I'm Abhijay Vashisth, working as a software developer at DLT Labs. And in this video, we're going to discuss enterprise level Solidity coding standards and security. In this video, we'll cover how libraries work in Solidity, importing source files, difference between send, transfer, and call, exception handling, and important aspects for Solidity security. So let's start off with the Ethereum libraries. Libraries are similar to contracts, but their purpose is that they're deployed once at a specific address and their code is reused using the delegate call feature of the EVM. This means that if the library functions are called, their code is executed in the context of the calling contract. That is, this points to the calling contract, and especially the storage from the calling contract can be accessed. As we know that a library is an isolated piece of source code, it can only access state variables of the calling contract. If they're explicitly supplied, it would have no way to name them. Library functions can only be called directly without the need to use the delegate call if they are view or pure functions, because libraries are assumed to be stateless. Since version 0.4.20, a library cannot be destroyed. In blockchain, transaction can change state of smart contracts. There are various kinds of state change that can happen in a contract. Sending Ether, which will update the balance of a contract, and changing data in contract will change storage root. Whenever user sends a transaction to a smart contract, which is internally using library contract, then state change happens on the smart contract, not in the library contract. This is possible with the delegate call feature of EVM. While using a library, a contract dynamically loads code from a different address at runtime. Storage, current address, and balance still refer to the calling contracts. Only the code is taken from the calling address. If a smart contract is consuming a library which have only internal functions, then EVM simply embeds library into the contract, which is known as the embedded library. On the flip side, if a library contains public or external functions, then library needs to be deployed. Deployment of library will generate unique address in blockchain. This address needs to be linked with the calling contract. Now, let's talk about importing source files in Solidity. Solidity supports import statements to help modularize your code that are similar to those available in JavaScript. However, Solidity does not support the concept of a default export. At a global level, you can use import statements of the following form. Import file name. This statement imports all the global symbols from file name into current global scope. This form is not recommended for use because it unpredictably pollutes the namespace. If you add new top level items inside the file name, they automatically appear in all files that import like this from file name. It is better to import specific symbols explicitly. The following example creates a new global symbol name, whose members are all global symbols from file name, which result in all global symbols being available in the format symbol name.symbol. Other ways to import source files are importing from GitHub, where URL to the Git repo can be specified, and importing from Swarm, using all the URLs supported by the Swarm. Since version 0.4.13, Solidity has one new important function, the transfer function. Here's the difference between send, transfer, and call functions. With address send amount, it was possible to send an amount to a specific address, but there are two problems. Only a small amount of gas is sent along, so the receiver can emit only one single event at max. It cannot be another contract that changes state variables or call again other contracts. So it's pretty safe by accident. If an error is thrown, send will return false and not propagate the error. Send is not deprecated, hence many developers have therefore defaulted back to recipient.call.value, that is the call function, which was merely a workaround and still returns a boolean on success or error. Now exactly this workaround received the name and fully propagates exceptions with the new function transfer. Transfer fully propagates errors on throw. Also, the Solidity by example documentation got updated and now uses the dot transfer function. Since version 0.4.13, we have a new exception handling technique in Solidity. Instead of simple throw, we now have revert, require, and assert. In this video, I'll walk you through the exact difference between the old and the new exception handling. First, to help separate these guard functions in your mind, imagine assert as an overly assertive bully who steals all of your gas. Then imagine require as a polite managerial type who calls out your errors but is more forgiving. With that mnemonic handy, what's the real difference between these two functions? Prior to the Byzantine network upgrade, require and assert actually behave identically, but their bytecode output is slightly different. If you look up either of those opcodes in the yellow paper, you won't find them. This is why you see the invalid opcode error, because there is no specification how a client should handle them. Require, as we know now, returns all the gas consumed, and we have the following examples given. We have now revert, which will still undo all state changes, but it will be handled differently than an invalid opcode in two ways. It allows you to return a value. Most smart contract developers are quite familiar with the notoriously unhelpful invalid opcode error. Fortunately, we can return an error message or a number corresponding to an error type. Also, it can refund any remaining gas to the caller. Currently, when your contract throws it, uses up any remaining gas. This can result in a very generous donation to miners and often ends up costing users a lot of money. Since Revert has been implemented in the EVM, it is plain old bad manners not to use it to refund the excess gas. So if revert and require both refund any leftover gas and allow you to return a value, why would you burn up gas using assert? The difference lies in the bytecode output. The require function should be used to ensure valid conditions, such as inputs or contract state variables, are met, or to validate return values from calls to external contracts. If used properly, analysis tools can evaluate your contract to identify the condition and function calls which will reach a failing assert. Properly functioning code should never reach a failing assert statement. If this happens, there is a bug in your contract which you should fix. In practice, use a few heuristics to help decide which is appropriate. If you have some complex nested if-else logic flow, you may find that it makes sense to use revert instead of require. Keep in mind though, complex logic is a code smell. Basically, require should be your go-to function for checking conditions. Assert is just there to prevent anything really bad from happening, but it shouldn't be possible for the condition to evaluate to false. Also, you should not use assert blindly for overflow checking, but only if you think that previous checks would make an overflow possible. While we approach the end of this video, it is essential to discuss about important aspects for Solidity security. Starting off with the security pitfalls, we have overflows and underflows. An overflow is when a number gets incremented above its maximum value. Solidity can handle up to 256-bit numbers, which is 2 to the power 256 minus 1. So incrementing by 1 would result into 0. Likewise, in the inverse case, when the number is unsigned, decrementing will underflow the number, resulting in maximum possible value. You can test the bug here. The underflow case is more likely to happen. For example, in the case where token has X token, but attempts to spend X plus 1. If the code does not check it, the attacker might end up being allowed to spend more tokens than he had and have a maxed out balance. For the people who were around in July 2017, this bug will be familiar. After all, it was the parity wallet hack, which cost users about $30 million. To prevent such manual anomalies, we will talk about Solidity visibility modifiers and their differences. First is public functions, which can be called by anyone, by functions from the inside a contract, by functions from inherited contracts, or by outside users. External functions can only be accessed externally, which means they cannot be called by other functions of the contract. External is cheaper to use because it uses the call data opcode, while public needs to copy all the arguments to the memory. Next comes private and internal are simpler. Private means that the function can only be called from the inside of the contract, while internal proves a more relaxed restriction, allowing contracts that inherit from parent contract to use that function. You can see the example on the right, which clearly describes all the modifier and the uses. With that said, keep your functions private and internal, unless there is a need for outside interaction. Solidity's call function, when called with value, forwards all the gas it received. In the snippet below, the call is made before actually reducing the sender's balance. This opened up a vulnerability which led the DAO attack. In simple words, it's like the bank teller doesn't change your balance until she has given you all the money before requested. Can I withdraw $500? Wait, before that, can I withdraw $500? And so on. The smart contracts, as designed, only check you have $500 at the beginning once and allow themselves to be interrupted. Note that reentrancy is not only an effect of ether transfer but of any function call on another contract. Furthermore, you can also have multi-contract situations into account. A call contract could modify the state of another contract you depend on. So the best practice is currently using message.sender transfer value. Another pitfall in the list is call stack depth. External function calls can fail at any time because they exceed the maximum call stack of 1024. In such situations, Solidity throws an exception. Malicious actor might be able to force the call stack to a high value before they interact with your contract. Note that send function does not throw an exception if the call stack is depleted, but rather returns false in that case. The low-level functions like call, call code, delegate call, and static call behave in the same manner. Now it's time to conclude the video with some security recommendations while writing a smart contract which every developer should take into account. Take warnings seriously. If the compiler warns you about something, you should better change it. Even if you do not think that this particular warning has security implications, there might be some other issue buried beneath it. Restrict the amount of ether. Restrict the amount of ether or other tokens that can be stored in a smart contract. If your source code, the compiler, or the platform has a bug, these funds may be lost. If you want to limit your loss, limit the amount of ether. Keep it small and modular. Keep your contract small and easily understandable. Single out unrelated functionality in other contracts or into libraries. General recommendations about source code quality of course apply. Limit the amount of local variables, the length of function, and so on. Document your functions so that others can see what your intention was and whether it was different than what the code does. Next is use the checks effects interaction pattern. Most functions will perform some checks like who called the function, are the arguments in range, did they send enough ether, does the person have tokens, etc. These checks should be done first. As the second step, if all checks passed, effects to the state variable of the current contract should be made. Interaction with other contracts should be the very last step in any function. Include a fail-safe mode. While making your system fully decentralized will remove any intermediary, it might be a good idea, especially for new code, to include some kind of fail-safe mechanism. You can add a function in your smart contract that performs self-checks like has any ether leaked, is the sum of the tokens equal to the balance of the contract, or similar things. Keep in mind that you cannot use too much gas for that, so help through off-chain computations might be needed there. If the self-checks fail, the contract automatically switches into some kind of fail-safe mode, which, for example, disables most of the features, hands over the control to a fixed and trusted third party, or just converts the contract into a simple give me your money back contract. The last is ask for peer review. The more people examine a piece of code, the more issues are found. Asking people to review your code also helps as a cross-check to find out whether your code is easy to understand, a very important criteria for good smart contracts.